Welcome to the second chapter of the A-star guaranteed course. This is Quadratics that we are looking at now. We had a brief introduction to this in the first video, which was chapter 1, algebraic expressions. So this one is like a more formal introduction, and we are going to look at this in a much more depth than we did in chapter 1, which was just factorization of this quadratics. So let's start with the definition. What are quadratics? A quadratic is a polynomial of a degree 2. What do I mean by degree? By degree, I mean that the highest power in a quadratic is 2. Well, highest power in an expression is 2, which makes it a quadratic. So highest power is 2. So the most common form that we'll see, ax squared plus bx plus c, where a, b, and c are some numbers. A, b, and c are some numbers, real numbers, and a is not equal to 0. What happens if a is equal to 0? Well, if a is equal to 0, then you have bx plus c. This is not a quadratic because the highest power is 1. X to the power 1 is x, so the highest power here is 1. So this is not a quadratic. I need the x squared term to classify it as a quadratic. Okay, now let's move on to solving quadratics. Okay, let's consider an example where we have x squared minus 2x minus 15. And I want to find which all numbers x solve this expression equal to 0. Now, as we learn in this chapter, there are like 2 to 3 ways which we can do that. One is middle term splitting, you can complete the square, or there is quadratic formula. So we'll go into that in much more depth later on. So to solve this, we are going to use the middle term splitting method. We are going to find two numbers which multiply to negative 15 and add to negative 2. If you don't know why we are doing this, you might want to check out the first video where we were factorizing quadratics. I've explained that there very well. So once we have that, what numbers can I pick? Well, it's not that easy to see, not that difficult to see that negative 5 and positive 3 do a good job, because negative 5 plus 3 is negative 2, and negative 5 times positive 3 is negative 15. So now I'm going to rewrite the expression as x squared minus, actually plus 3x, and you'll see why. And now I'm going to put minus 5x right here, minus 15. The reason I use this order is because 5 and 15 can combine easily, and you'll see something happening. You probably already have visualized it in your head. So this is equal to what? X times x plus 3 and minus 5 x plus 3. So this is what's happening. I can factor out 5 from both of these. So that's why it makes sense to put 3 on this side and negative 5 on that side. You could have also did that the other way, and you could say, yeah, 3 and 15 also have 3 in common. So yeah, both of them work. Sometimes it happens that you have to put them in a specific way, like I did here. But in this case, it was not required. And here you factor out x plus 3, and what you get is x minus 5. So, and we set this equal to 0 because that was our original expression. Once we have that, I'm going to scroll down a bit. We see that the only way this expression can be 0 if one of these brackets are 0. So I need either x equals equal to 3. This implies either x equals negative 3 or x must be equal to 5. These are the only two solutions. X equals 5 would make the second bracket 0, x equals negative 3 will make the first bracket 0. So that's basic middle term splitting and solving a quadratic. And you guys have seen this enough now, so we'll move on to a different thing called completing the square. Sometimes middle term splitting is not possible, so we have to use other methods to factorize or solve a quadratic expression, and one of those methods is completing the square. This is a very famous method and it's not very difficult to understand. It just takes like a couple of practice problems. So I'm going to write an expression. What I'm going to write is x squared plus 8x. And of course, if I set this equal to 0, some of you might be able to tell me instantly that, well, the solution here is quite simple. If I just factorize normally, then what I see is that x times x plus 8 equals 0. This implies either x is 0 or x equals negative 8. That's the only way I can make this expression equal to 0. And yeah, that would be completely correct. So sometimes things are more complicated and we might have to use completing the square, which is what I'm going to show you just now. I'm going to use the property I've mentioned above, this one. And what I'm going to say is that this is same as saying x plus b is 8 in this case, and b over 2 is 4. This is same as x plus 4 squared minus 16. Why? Because that's the square of 4. So x plus 4 squared minus 16 is same as this. And now I need to set this equal to 0. How will I solve this? I'll have to take 16 to the other side. So I get x plus 4 squared equals 16. This implies x plus 4. I take square root on both sides. Gives me plus or minus 4 because square root of 16 can be positive 4 or negative 4. So if I have positive 4, then x equals 4 minus 4, which is 0. Or if here I have negative 4, then x equals negative 8, because that would be negative 4 minus 4. I can write this more clearly for you. X equals plus or minus 4 minus 4. So that means x equals 0 or x equals 8. And we get the negative 8, sorry. And we get the exact same solution. So this is called completing the square. Now here I've taken an easier example because I have not added a constant to 8x, like there could have been plus 3 or there could have been a different number, and there could have been a constant here as well. I could have had like number 3 or number 6, number 9, anything here. What would we do then? So let's look at a harder example now. Also, I want to make a point that not all quadratics have a solution, at least not a real solution. Like here we have 2 real solutions. It is possible for a quadratic to have no real solutions. And we'll see an example. I can make a graph and I can explain to you very quickly. I've drawn a quadratic here. This is not perfectly drawn, but it's what a general quadratic looks like. And this has some equation. I don't know what it is. I'm going to say ax squared plus bx plus c. And I want to see where this quadratic attains a value of 0. So where is y equal to 0 in this case? Y equals 0 is the x-axis, but this quadratic never touches the x-axis. So this quadratic has no real solutions. No real solutions. It never touches the x-axis. So that's what I meant to say, that some quadratics do not have real solutions. Okay, now let's look at a harder example of completing the square. Okay, so now we have this example. Consider this, and I'm going to say it's equal to something. And how do I complete the square for this? Because this is not of the form x squared plus bx, is it? This is of a form ax squared plus bx plus c. Well, I can simplify things for myself. Firstly, I'm going to take a common factor. I'm going to divide by 3 because I want to get rid of this a. I want to get rid of 3. So I'm going to divide this expression by 3. So I'm going to take 3 out. And then I'm going to say this is equal to x squared plus 2x. And then I'm going to close the brackets and I'm going to put 1 as it was. I'm not dividing 1 by 3. I just care about the first 2 terms. This is just a constant term. It will not make much difference to us. Now I know I can complete the square for this term, which will be what? 3, open brackets, x plus 1 squared, because 2 divided by 2 is 1. And then I need to subtract 1. And we have already proven that these two things are equivalent. So you know this works. And then we have plus 1 at the end. We have still not solved the quadratic. We still need to do more work here. So what do? We now expand this bracket again. 3 times x plus 1 squared minus 3 plus 1. Right? That's how we expand the brackets. We simplify this to 3 x plus 1 squared minus 2. And suppose this expression was equal to 0. Now if I want to solve this equal to 0, this is trivial. And we did this like in the last example as well. This implies 3 times x plus 1 squared equals 2. This implies x plus 1, I'm going to scroll down a bit, x plus 1 squared equals 2 over 3. So x equals plus or minus square root of 2 over 3. That's what I'm going to do on both sides, minus 1. And those values that you'll get two values, and those will be your solutions. So this is what really completing the square is. We have seen the hardest type of example where we have a constant besides the x squared term. So what you'll do, you'll first get rid of that constant, you'll factor it out, 3x squared plus 2x. Suppose if I had 5 instead of 6x, I had 5x. Then here I won't have 2x, I would have 5 over 2x. So instead of 2x, I would have had 5 over 2x, and then I would have done the same thing as I do here. I can just show you very quickly. Then I know I need to get rid of 3, even though 3 and 5 do not have a common factor. So what I'll do is this is equal to 3 x squared plus 5 over 3x plus 1. Now what do? I of course divide the b term, which is this one, by 2. So that would be 5 over 6. So this is same as 3 x plus 5 over 6, put it in brackets, square, and I subtract the square of this term. If we go back above, that's what we do. We half the middle term, x plus b over 2 squared, and then we subtract b over 2 whole squared. So that's what we are going to do here. And I'm going to subtract 25 over 36, and then plus 1 remains as it was. Now I expand the brackets, 3 times x plus 5 over 6 squared. That would be my first term, and then I have 3 times negative 25 over 76. So that's negative 75 over 36 plus 1. You set it equal to 0, you make x the subject, and it's easy from there. So now, and you'll do this, you'll get the two solutions. So that's literally what completing the square is. And now I'm going to look at something called the quadratic formula. Now, this is our beloved quadratic formula. You can see it on your screen. Looks like a long expression, doesn't it? Seems very hard to remember as well. No, it's not that hard to remember. With some experience, you will definitely be able to remember it. What I'm more interested in is, where does this formula even comes from? Some of you may have guessed it. It actually comes from completing the square. This is the derivation. Now this looks very scary. I promise you it's not. Let's go through it step by step. So this is the derivation of the quadratic formula, and it looks scary, but it's not scary at all. And it's basically just completing the square for the general expression ax squared plus bx plus c. So let's go through it step by step. Ax squared plus bx plus c. You try to complete the square. Now you'll see they have divided even c by a, and that's an equivalent way of completing the square. I prefer not to divide a by c, and I try to keep a outside. But you can do this, it's equivalent. They divided both sides by a, and we assumed a was not equal to 0, so that's possible. Then they took c over a to this side. As you can see, the c over a just went to this side, became negative c over a. Now we are left with the LHS. We know this is easily, it's easy to complete the square here, which is from the identity. They did that. X squared plus b over ax plus b over 2a squared. They did it in a slightly different way, but essentially they get that square which they wanted, and they get one term to the other side. You simplify that term, you solve for x, and you'll get basically the quadratic formula, which is negative b plus minus square root of b squared minus 4ac over 2a. It's nothing more than completing the square for the general expression ax squared plus bx plus c. If you practice completing the square for some examples few times, you will essentially realize that this is nothing difficult at all. So this is the derivation of the quadratic formula. Now, to find the solutions, let's say if I have an expression which is x squared plus 2x plus 1, and this is the easiest expression, easiest quadratic ever, because this is just x plus 1 whole squared. So I know the solution is negative 1, x equals negative 1. Does quadratic formula work here? Let's test. What is quadratic formula? X equals negative b plus minus square root of b square minus 4ac all over 2a. And what is negative b here? That would be negative 2. plus minus square root of b squared. What is b squared? 4 minus 4 times 1 times 1. A is 1, c is 1. So I expand the square root and I divide the whole thing by 2 times a. A is 1. So 2 times 1 is 1. And I get the solution as negative 1 plus minus square root of 4 minus 4 is 0, which means the solution is only negative 1, but twice. Equals negative 1 twice. It's a repeated root. So that's basically what the quadratic formula is. It's nothing more than that. It's more important to see where the quadratic formula comes from, which is completing the square for the general expression ax squared plus bx plus c. So I'd recommend that you practice completing the square quite a fair bit. So one more last point I want to make here before we continue is that if this expression inside the square root sign was negative, suppose let's say this was negative square root of 25, then no real solutions. No real solutions. Why? Because how do you square root negative 25? Negative was inside, sorry. Then no real solutions. So that's it. Now we are looking at functions. What is a function? A function is of a form, let's say f of x. You can also have g of x or h of x. You can use any letter. What this is saying is, and there will be some expression. So let's say x squared minus 5. What is this function actually saying? It says put a number x and you'll get the computation of this expression as an output. So if I input 3, if I say f of 3, then I get is 3 squared minus 5. And what I get is 4. So you might ask, isn't this same as y equals x squared minus 5? Isn't f of x equals y? You can think about it that way. But when you say something is y, right? So usually when we see y equals x squared plus 5, x squared minus 5 or x squared plus 5 doesn't matter. It's one formula, right? It's one formula. Y equals x squared plus 5. A function is not a formula. A function is not exactly a formula. You'll see what I mean by that. Right now what I wrote, f of x equals x squared minus 5, the first statement, looks like a formula. If I use a different pen, and let me just bring that in. This seems like a formula, right? Like how is it so different from y equals x squared minus 5? Now imagine I told you I construct a function. Let's say my function is g of x. I'm going to construct a different function. And I'm going to say that g of x equals x squared minus 5 if x belongs to the list 1, 2, 3. If x is 1, 2 or 3, then I'll compute this expression. Or g of x will be equal to simply x if x does not belong to 1, 2, 3. So if I were to compute g of 4, then that does not belong to 1, 2, 3. So g of 4 is just 4. But g of 3 would be computed using the first formula, which would be 3 squared minus 5 equals 4. So that's really the difference between using the y notation and the functional notation. You can separate how the function will act for different values. If I had not specified anything, then the function acts in the same way for every single value. But if I'm specifying how the function will act for different values, then you'll compute the values differently. So now I'm going to take the concept of minimum and maximum value. In front of you, there are two graphs of the form ax squared plus bx plus c, which is the general form of a quadratic. But a quadratic can be a happy shaped or a sad shaped. So you see there is a smiling face, which is the first one, and there is a sad face, which is the second one. Now, how do we decide which one is the first one and which one is the second one? The thing is, if in the expression ax squared plus bx plus c, if a is a positive number, then we'll have the first expression, a happy face. And if a is smaller than 0, then we'll have a sad face. A quadratic with positive a will have a minimum value. A quadratic with negative a will have a maximum value. Now, why does that work? Like, what's the reasoning behind it? Suppose a is greater than 0. Now, let's see how the expression reacts as x tends to infinity. Let x tend to infinity. Now, what will this expression evaluate to? So a times infinity squared, whatever that is, don't use this informal language in the exam, times b times infinity plus c. We'll see this will tend to infinity, right? This will still go to infinity. Now don't say this is like larger than infinity or something like that, because we can't really, this course is not about infinity. What we are saying is that this expression cannot have a maximum value because it's tending to infinity, and infinity is not a real number. So it's just going to infinity. So if a is positive, then the expression can only have a minimum value. It will not have a maximum value. It will always have a minimum value by the nature of quadratics. And the same thing goes the other way. If a is smaller than 0, if I just change the sign, and if I just say a is smaller than 0, what really happens is I get negative infinity squared, right? Infinity squared by a negative number. So this will tend to negative infinity in that case. Because even though even though b might be negative, b might be positive, since there is like negative infinity squared term here, and I have like positive infinity here, this negative infinity squared is much bigger. So the expression will indeed tend to negative infinity. What does that mean if it tends to negative infinity? It can only have a positive maximum value, and it will have to go, it will not have a value. It will not have a minimum value because it's going to negative infinity. You can't get smaller than negative infinity. That's the exact reason. So it's by seeing how the expression behaves as x tends to infinity. Question arises, how do I actually find the minimum point? Now there is something important to notice here about minimum and maximum points. Minimum and maximum points will lie at the x value, which is negative b over 2a. And this point is also exactly between the two roots. The two roots are the two solutions which satisfy ax squared plus bx plus c equals 0. And if the two roots are the same, then that point itself is the minimum and maximum point. That's a mouthful of words, right? Let's see what I mean by that. If I have the expression x squared plus 2x plus 1, the minimum is at x equals negative b. What is negative b? Negative 2 over 2 times 1, because a is 1, and this is same as negative 1. Now, what were the roots of x squared plus 2x plus 1? As I told you, this expression was same as x plus 1 squared, which means if this was equal to 0, that means x would be equal to negative 1. So negative 1. And what you see is negative 1 would be a repeated root because this is a quadratic, x plus 1 times x plus 1. So what have I said here? If the two roots are the same, which is in this case, then that point itself is the minimum or maximum point. In this case, that's the minimum point, since the coefficient of x squared is positive. So you see, the third point is satisfied like that. And we also saw that the first point is satisfied like this, negative b over 2a. Now, what did I mean by this point is exactly between the two roots? In this case, I have repeated roots. If I did not have repeated roots, let's say a graph of x plus 1 times x plus 3. Let's consider this expression, new expression. So I'm going to draw a line because it's a new expression. What does this evaluate to? This evaluates to x squared plus 4x plus 3. Now, its minimum is at negative b over 2a, right? This is equal to negative b over 2 times 1. So this is same as negative 2, right? And its roots are negative 1. Its roots are negative 1 and negative 3. Why? Because if I were to solve this expression to 0, I know x would have to be negative 1 or negative 3. And where does the minimum lie? What's the average of negative 1 and negative 3? Negative 2. So this is equal to the x. So minimum value will lie at x equals -2, which is exactly between -1 and -3. So these are all the 3 points which are now satisfied. Hopefully you understand this. One fun trick is that you can find the minimum and maximum from completing the square itself. If you were to complete the square for this expression, you will have x plus 4/2, which is 2, x plus 2 squared minus 4 plus 3. And you already know when you complete the square, the x value which makes this bracket 0 gives you the minimum point. So this is at minimum at x equals 2. X equals -2, I mean. Because that's the value which will minimize this bracket, equal to x plus 2 whole squared minus 1, right? I want to minimize this expression. Minimize this expression. Minimize the value. How do I do that? I need to minimize the value of this bracket. Now, since this bracket is squared, I know this bracket is greater than or equal to 0, just this bracket, because anything squared is greater than or equal to 0. So to minimize this expression, I need to have this bracket equal to 0, which only happens when x equals -2. Minimum value would be -1. So in this case, the y would be -1. I hope that's right. I can just check. So if I put -2, -4, 4 times, yeah, 4 minus 8 is -4. Yeah, exactly. If I had a graph of this one, my roots are where? My roots were -1 and -3. So this graph goes something like this, -1, -3, and this graph has some sort of thing like this. And -2 is your thing. -2, -1 are the coordinates of this minimum point. I've not drawn the quadratic perfectly, but you get the point. Now the last thing in this chapter which we need to talk about is discriminant. And before we do that, we need to get back to our beloved quadratic formula. You know how I talked about that if the term inside the square root is negative, then it's not possible to have real roots, because how do you square root a negative number? So then there won't be any solutions. So what we are interested in is considering this thing, b squared minus 4ac. So if b squared minus 4ac in a quadratic expression, ax squared plus bx plus c, is smaller than 0, which means it is negative, then no real roots at all. No real roots. Remember that. If b squared minus 4ac is equal to 0, is actually equal to 0, I hope you can see my screen, yeah, then there are repeated roots. So let's say a root like 1 would be repeated twice. No unique roots, but 1 repeated roots. Repeated roots. But then what will happen if b squared minus 4ac is positive? Is positive. Then I have 2 roots, 2 real roots. Now we can think about why that happens. Why that happens? If b squared minus 4ac equals 0, if this is equal to 0, then the quadratic formula is just left as -b over 2a, right? And plus or minus disappears. So plus or minus 0, right? It doesn't make a difference. So then we have repeated roots. Now if that is positive, if I have another number instead of 0, let's say it's 3, then I have, you can see there will be two equations. One would be -b over 2a plus 3, other one would be -b over 2a minus 3. So I'll have 2 real roots. That's basically what discriminant is. I'm just going to quickly show you what happens if the discriminant is positive. What do the graphs look like? You probably can guess it. If I have 1 root, so the graph might look like something like this. Repeated roots. It will just touch the x-axis and it will go up. So this is b squared minus 4ac equals 0. If b squared minus 4ac is less than 0, if it is less than 0, then the graph will never touch the x-axis and it might look something like this. So b squared minus 4ac is smaller than 0, no roots. It has to be perfectly symmetrical. My drawing is bad, so excuse me for that. And if it's a general quadratic which has a positive discriminant, then it will look something like this, and I'll have two solutions. As you can see, this is where y equals 0. This is your y-axis, this is your x-axis, this is 0. So these are your two roots, and here b squared minus 4ac is actually positive. Hopefully I'm not hiding anything. Yeah. And the roots are real. Two real roots. And that is your chapter completed. These are all the concepts. As usual, you have to go through all the examples in your book and you have to solve as many questions as you can. Theory is one thing, practical is another. You solve as many questions as you can using these concepts that I've known. Let me know if you don't get an A star. It's not possible. It's not possible. I have oversimplified every single concept for you. So I'll see you in the next video. Thank you very much.